Hello, I want to welcome you once again to our lecture series. Today we'll be looking at the physical states of matter. In this chapter, our main focus will be on the physical properties of matter. That's basically what we're going to be looking at. And we're going to be using this chapter to introduce these physical states and to know their distinct physical properties. And let us take it off from there. Now, my angel of the blessed memory, some of us might have heard about her. She was inspirational in writing most of the best books that inspire people to live a better life. Look at one of her quotes. She says, "You will face many defeats in life, but never let yourself to be defeated." And I usually tell my students this all the time I get into the class. I tell them, no army of this world can overcome a day whose time has come. The only person that can defeat you is yourself. If you refuse that you cannot be defeated, no human being can defeat you, even when you face defeat. But you yourself will never be defeated. This is a good message from Maya Angelou, 1928 to 2014. Let us delve very fast into our lectures. Today we have two important learning objectives that we're going to look at. One, we're going to understand what the kinetic and molecular theory of matter is and use it to describe the properties of various matter. The word kinetic means movement, so we're going to try to understand matter from the point of particulate movement. That's exactly what kinetic theory is. And again, we're going to classify the changes of matter as either exothermic or endothermic. You remember earlier, we made mention of these types of reaction, but in this case, we're looking at only these physical changes as exothermic or endothermic. Let us take it off from there. Of course, matter exists in three physical states: the solid, the liquid, and the gases. Now, they are arranged as their level of energy is. Now, the gases, of course, have no definite shape, no definite volume. They're always moving apart. Now, let me put something here. This my arrow shows you the energetic strength of these molecules. So this is increase in energy. Oh, rather, this is a wrong arrow. I should use it. Let me put it this way. Increase in energy. Now, the gases are the most energetic particles because they move about all the time. And because they move about all the time, they have really very high kinetic energy because they're always moving about. This is followed by the liquid, which move about not as much as the gases, but the solid, which are always compressed and stays close to each other. They're always rather condensed, stays very close to each other, and don't move about as much as the other two previous states. And these are very good examples. So here we have an ice, liquid water, and this is probably a steam. A steam just means gaseous water. That is the three states. So let's look at those properties. Let's look at what those properties are. Now, so what are the physical properties of these three states of matter? Density. Let's start from the density. Now, the solids are very dense state of matter. They're very dense. Of course, you remember again, density simply means the ratio of mass to volume. So what it simply means, the gases are dense because they don't occupy a lot of volume, but they are very heavy. They have a lot of mass, and because of that, the density is very high. The liquids are in between, and the gases have very low density. And the reason why gases have very low density is because they have what? The gases have very high volume. They occupy whatever volume of the container. And if you look at this, in this reaction, if the volume is too high, if the volume is high, the density is going to actually be low. That's exactly what you see from this equation. So the very really high volume, and that's why the density is really low all the time. Shape. The solid have a definite shape. Solids can be either a square, a triangle, a rectangle, have a definite shape. Now the liquids have indefinite shape. However, they take the shape of the container. They take the shape of the container as it feels it. Now, if you look at this structure, you see this is a liquid. This container, this is like, will I say a cup, or you can call this a beaker. The water feels to this extent. It doesn't feel everything. So that is how water behaves. Now the gases have indefinite shape. What they take the shape of the container and they will fill it completely. So what it means is that whatever be the volume of the container will be the same volume of the gases, because they'll take total control of the volume and fills it completely. They fill it completely. Compressibility. Solids are very difficult to compress because they are very condensed. It is difficult for you to do that. Liquid, you can easily compress them a little bit. Gases are highly compressible because there are a lot of spaces in between the atoms. So if you start compressing it, it's going to be coming closer and closer each other. So easy to compress the atoms of gas molecules. And then the thermal expansion. Now, when you heat these guys, they respond a little bit to heat and begin to move about. Now, the liquid are in between, but these guys will easily pick up kinetic energy and begin to move about easily. Because that kinetic energy is supplied by heat, they begin to move about very easily. So they have very high thermal expansion. They easily respond to the change in heat. Then lastly, so one other thing I want to include there is, I didn't have it in my note, but we can include something. This is cohesive forces. Cohesive forces is force of attraction between different particles. Or rather, I would say adhesive forces. Sorry, my bad. I want to say adhesive forces. Forces of adhesion. What am I saying? That was correct. Not cohesive. I mean cohesive. I don't know why I said I was wrong initially. The cohesive force. A cohesive force is a force of attraction between like particles. Like if water molecule is attracting another water molecule, that is a cohesive force. Cohesive forces are the highest in the solids. These guys also are in between, the medium. Whereas at this point, I'm going to take away this. I've made explanation with this. I'm going to take it away. For the gases, their cohesive force is very low. Gas molecules rarely attract each other because they want to keep moving about. They don't take responsibility for individual atoms and they just keep moving. So what it means, and that is the reason why they fly about and go their own way. So energies of matter, this will now bring in some of those things I talked about already. Now, there are two main energies of matter when it comes to mechanical energy. One is the kinetic energy and the potential energy. Kinetic energy simply means energy in motion. You would have known this. So any object that has a speed, v, let me say, will have a kinetic energy. So and what is the implication of kinetic energy? When a particle starts moving, if you maybe hit a particle, it gains some kinetic energy and begins to move around and dance around. Now, at a point, this movement will result to what we call a disruptive force. A disruptive force is a force that will result from motion. And this motion will finally lead to what? The breakage of the intermolecular force. And when you get to this point, the breakage of this intermolecular force will result to the change of a particular molecule from one physical state to another. If it is a solid, it's going to break. You're going to disrupt the intermolecular force, break it down. It's going to change to liquid. If it's a liquid, if you now heat it more, you break the intermolecular force, hydrogen bonding, holding the water molecules together, and they begin to escape of gases. Now, the second type of energy we'll be talking about here is potential energy. This is energy due to attraction or repulsion in a molecule. When molecules are attract or repel themselves, that type of energy is called, now it can be two types. Attractive force, it can be a cohesive force, like I said earlier. It's a force of attraction between particles of the same kind that will hold particles of the same kind together in that intramolecular substance, pure substance. Holding it together is a cohesive force. Adhesive forces are forces that hold particles of different kinds together. So a good example, like I said earlier, water molecule in our last lecture, water molecule, we can see water has a strong affinity for the glass tube, and that is why it has a high capillary action, because it can attract another atom or another substance that it is not of its kind easily and adhere to it. And that's what we mean by adhesive forces. So these are the forces that actually determine the physical states of matter. Now let's now get into the big one, the kinetic and molecular theory of matter. You see, having told you that kinetic simply means movement, we try to use the ability of matter to move to explain the actual behavior of matter, the properties of matter. Now, there are important assumptions that we're going to look. Now, the mother says they include the following assumptions. There are about 5 of them. Number 1, it says matter is made up of tiny particles. Yes, this is very correct. Every matter is made up of tiny particles called molecules. There are particles making it up. It is made up of it, and these molecules are made up of atoms. Every matter is made up of this. Now, the particles of matter, of course, are always in constant motion. And because they're always in constant motion, in fact, every matter, at times you can see some substances, they are not moving. That doesn't mean they don't have kinetic energy in them. It is the degree of this movement that decide whether a matter is solid, liquid, or gases. In fact, when they are moving so fast that they break the intermolecular forces, they become gases. When they are moving in between, we say they're liquid. And when they're not moving as much as we think, maybe when they're moving a little bit, that is actually a characteristic of the solid. So every matter is in constant motion and possesses a level of kinetic energy. And it is this kinetic energy that determines their physical state. It determines the physical state of matter. And like I said again, this energy, gases have more energy than the liquid. Liquids have more energy than the solid. Now, the particles of matter also possesses the potential energy. And this potential energy, of course, is as a result of that attraction and repulsion we said earlier. Now, because every matter is made up of this molecule, and these molecules are made up of atoms, and these atoms are held together by bonds, there are potential energy that is resident in these bonds. Now, and again, the average kinetic energy. Now, remember, we say all matter move. How do we determine the temperature of this matter? It is by measuring the average kinetic energy of this matter. And as you increase this average kinetic energy, the temperature increases. That makes sense. As you increase the kinetic energy, the temperature increases. That makes sense, because the more the temperature increases, the more these guys are dancing around, colliding with each other, and then potential energy increases as well. Now, the last but not the least, the particles of matter transfer energy from one another during collisions. Now, when you heat up a matter or they pick up an energy, they begin to move. Now, when they begin to collide with one another, what I simply do, energy is neither lost or gained. Remember, according to the law of conservation, what I simply do is that they transfer this energy from one particle to another during collision. And of course, no energy is lost. What they just do is transfer energy from one form to another. And that is exactly what we call the kinetic and molecular theory of matter. So now let's begin to apply this to the change of state. A change of state, of course, is attained either by heating or cooling or changing the pressure. What it simply means is that by changing the kinetic energy, remember, energy due to movement, which is proportional to temperature, but changing the kinetic energy of matter, we can easily change a matter from one state to another. Of course, this is commonly accompanied by adding or removing of heat. If you're adding heat or if you're removing heat, you're going to change the state. Now, the change of state that is caused by addition of heat, if you're going to add the heat to a substance and facilitate the change of state, that kind of process is said to be an endothermic process. And in an endothermic process, actually, matter is changing from, in an endothermic process, matter is changing from low energy state to a high energy state. What do I mean? A good example is this. If matter is going from, let's say, a liquid to gas, it is going from liquid, which is low energy, to gas, which is high energy. Such a process is an endothermic process. And if matter is going from liquid to gas, that is actually vaporization. And that vaporization process is an endothermic process. Now, on the other hand, the change of state that involves the removal of heat, whereby heat is being removed, we classify it as an endothermic process. And in this process, what is actually happening there, to make it easy, is that you are having two states of matter. Matter is changing from high energy. Remember, this one is from low to high. This is from high to low energy state. And from any high to low energy state remains exothermic reaction. A good example, if we do the opposite of what we did, okay, if matter is changing, let's say from high energy, if matter is going from gas to liquid, So when a matter is going from gas to liquid, what does that tell you? It's an exothermic what? Process, because it's going from, so, and if it goes from gas to liquid, we're simply talking about condensation or liquefaction. This is actually called condensation or liquefaction, because it's going from, and this is an exothermic process because it's going from high energy state, please, I'm going to try this well, going from a high energy state, this is gas, to a low energy state. So these are those changes of states that we need to be familiar with as we move on in this class. So I have a very good diagram that explains these different types of changes of state. Now, of course, like I told you, in an endothermic reaction, the change of state is from a low energy to a high energy state. And look at those processes that occur, and then you need to be familiar with those terminologies about these names. Okay, so let's see what they are. Now, let's start from solid. If a solid is going from solid to liquid, solid is what? Solid means low, to liquid means high energy. Low to high is endothermic reaction. And this process simply means melting or fission. If you don't want to call it melting, call it fission. If a solid is going to a gas, it's going from low again to high. This is also endothermic, and this is called sublimation. You know substances that can undergo sublimation. Good example is the dry ice. Dry ice is solid carbon dioxide. The solid O2 can undergo this. There is also iodine can do this. Even naphthalene can also do this as well. Then now, if you go, so if a substance is going from from liquid to gas again, it's going from what? From liquid to gas again. Now remember this, if anything goes from liquid to gas, it now becomes low to high. Remember, in this case, liquid becomes low, this becomes what? High. So again, look, from low to high or liquid to gas again is an endothermic process, and this is also called evaporation or vaporization. If we take that to also this side as well, in an endothermic process, if you look at all these processes, it's going from again, like I said earlier, let me highlight this, it's going from high to low in each of those processes. Let's look at it. If a gas goes to a liquid, a gas is more energetic, more or high, you can say high energy to low energy. Now, what do you see here? You see that this becomes liquefaction or condensation. If you also go from gas to solid, this is called deposition or condensation. This again is high to what? Low energy state. And again, if a liquid is going to solid, again, it's going from high energy state from liquid to low. And again, this is called freezing. So you need to be familiar with some of these concepts, and we're going to use them in solving a few problems as we move on. Boiling point, of course. The boiling point of any substance is the temperature. It's a temperature. Boiling point is actually a temperature at which the vapor pressure of that substance is equal to the prevailing atmospheric pressure. The atmospheric pressure here we're talking about is either 1 standard atmosphere or 760 torr. So when a substance is heated until the vapor pressure has equals to the atmosphere, we call that its boiling point. And liquid will boil at a higher temperature, more than their normal boiling point, when the external pressures are high. If the pressures are too high, liquid will boil at a higher temperature, and vice versa. So if the pressure is low, liquid will boil at lower boiling point. And what that simply means is that, remember, the higher you go, the lower the pressure, and the lower the pressure as you go up and the altitude, the lower the boiling point of water. So pressure decreases with increase in height, of course. Pressure will decrease with increase in height, and as a result, water will always boil at a lower temperature at high altitude. That's why if you see those who live in high altitude, you see that water boils actually at lower temperature. And we're going to see that in the next slide. If you look at the variation of boiling point, the variation of boiling point of water in different elevations. Let's see what happens here. Now, let's try to see. In San Francisco, the elevation is about at sea level, at sea level. Water boils at 100 degrees Celsius, just like we are here in Yakima. At Salt Lake, Utah, the elevation above sea level is about 4,390. Water begins to reduce, the boiling point 95.6 degrees Celsius. Now, as you keep going down, look at this. If you go to Everett, which is the tallest mountain in the world, look at the height, 29,029 feet. above sea level, water begins to boil at approximately 76.5 degrees Celsius. So the higher you go, of course, the higher you go, the lower the pressure. And the lower the pressure, of course, the lower the boiling point of liquids. And this is an important thing you need to know, and it can show up as a multiple choice question. Let's begin to solve our problem immediately. It says, identify the term that describes the change of state listed and determine whether it is exothermic or endothermic physical change. If a solid is going to a liquid, remember how I told you the best way to figure out this is, if a solid is going to a liquid, this solid has less energy. This gas has what? More energy. So from lower energy to now, I can take you back to this a little bit. No, I was too fast. Okay. You see that? If it is going from less to more, it becomes what? Endothermic reaction. That's less to more. So in this case, we're looking at what? It's going from less to more. So it's an endothermic reaction. And if a solid goes direct to gas, we call this sublimation. This is called sublimation. And then sublimation is an endothermic process. Is an endothermic process. Again, let's look at this one. It's going from liquid to solid. Again, liquid has more energy than solid. This is less energy. And if you're going from more to less, remember that is exothermic. And if this don't happen, if you're gonna, this is like what happens in your fridge. You put your water in the fridge, it becomes solid. This is actually called what? Freezing. You are freezing the liquid, and freezing is actually an exothermic process because it needs, you're actually going from a more energetic state to a less energetic state. And again, let's look at this one. It's going from gas. Gas to liquid means more to what? Less energy. And more to less energy again is exothermic. And when this thing happens, if a gas goes to liquid, what it simply means, it is condensing. And this is called condensation. And condensation, of course, is an exothermic process. We go to the next one. The same question again. We identify the term that describes the changes of listed and tell me whether it's an exothermic or endothermic process. If you're going from gas to solid, again, you're going from more to less. Anytime you're going from more to less, it's going to be exothermic. And what do you call this? When gas goes to solid, we call it deposition. This is called deposition or condensation. It can also be called condensation. And this is an exothermic process. If a liquid is going to a gas, this liquid has less energy. This is going to a gas more, less to more energy is simply endothermic process. And when this thing happens, if a liquid is going to a gas, remember we call this what? This can be an evaporation process or vaporization. And since it's going from less to more energy, it is an endothermic process. An endothermic process. Again, if a solid is going to a liquid, solid has less energy than liquid. Liquid has more energy. So what again, if you're going from less to more, is an endothermic process. And when a solid becomes liquid, what I'll simply here, we're just simply melting the what? The solid. So this is called melting. And the melting process is actually what? An endothermic process. An endothermic process. And that is how you do this problem. Now, the last problem we're going to be addressing here, I told you this is a short lecture. It says, why does sweating, this is a common sense problem, and what we see every day, why does sweating bring about cooling? And explain what physical change is involved. Now, why does it involve, why does sweating? Sweating means evaporation. Remember, let's understand. Sweating simply means the water in your skin is being converted to what? Water is being converted to gas. That means it's going from liquid, right? That's exactly what it means. Remember again, if you're going from water means what you're going from less energy to what? More. Oh, this my gas should just be 1s. Okay. To more. So this is an endothermic process. So of course, we know this process to be an endothermic process because it's going from less to more energetic state. So he says, why does it bring about cooling? And I explain what physical change involves. So the physical change involved is an endothermic process. I've done gas is changing from solid to liquid. So we can from liquid to gas. Yeah, that's what's happening here. I have to just say liquid. Liquid, let me just say, to gas. Endothermic process. Now, why does this thing happen? Let's say the reason. There are two ways you can explain this as a test student. There are two ways. One, the first one is that you can say it this way, is that evaporation brings about cooling because it's an endothermic process. So it is an endothermic process. Every endothermic process requires energy. That requires energy for it to occur. And this energy is this energy. Okay, I should put this energy. I think that will be the best thing to do. Is supplied by the body. Then the body actually supplies this energy. Yeah. Which loses it. Which loses heat. Yeah. And hence cools down. So it's an endothermic process because someone has to give it that energy. So what it means is that that energy was actually lost by the body, which it gives these molecules of water, which now gains it and begin to move away. So, and that is why the body cool. Or I like also explaining this way now. You see, what is evaporation? As molecules of water gain energy, that's what is happening here. As they gain energy from the body, as they gain energy from the body and move out and become gases. So what happens here? The overall kinetic energy it has overall kinetic energy falls. So let me try to make sure the English is correct. It says, as molecules of water gain energy from the body and becomes gases, the overall kinetic energy level of the sweat, energy of water, or your sweat this time. Remember, so if you have like 10 sweat, 10 molecules of water, and 5 of them goes, what happens? It falls. You know, it falls. So the overall kinetic energy of water or sweat drops. And when this thing happens, when there's a drop in kinetic energy, there will be cooling. Drops. Hence, cooling occurs. That's exactly why evaporation causes cooling. Okay, just a very good example is that if you started with, let's say, 10 molecules of water, let me just use an animation here. So let me say there were 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me say 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then they gain energy, and some of them now escape as gases, and it is remaining 5. 1, 2, 3, 4, 5. So you have 10 particles here representing energy, and now you have only 5. What that simply means is that something is lost. About 5 molecules of water is lost. So if you have total of 10 kinetic energy and you are left with 5 kinetic energy, remember we say kinetic energy is proportional to temperature. This simply represents a drop in the temperature, and that is why sweating or evaporation causes cooling. Wow, it has been a good ride in a short lecture. Thank you once again for listening, and I'm going to see you next time in the next lecture in this module. Do have a wonderful day ahead, and bye.